So welcome back, students. Now we'll study in details about the Fermi Dirac distribution function. Okay, so the Fermi Dirac distribution function. Fermi Dirac distribution function. Okay, it will be a graph actually. So how will the graph look like? So we'll study it right now. Okay, so let's see. So that will be a graph. Okay, so let us draw it. Here along the y-axis there will be, means what is the Fermi Dirac distribution function? This is the this is the Fermi Dirac distribution function, FEI versus EI we are plotting. Okay, so along this there is FEI, okay, and along this there is EI or E, whatever. Okay. Now what is the Fermi Dirac distribution function? FEI is equal to 1 by e to the power of EI minus EF by KVT plus 1. Okay. Achha. Now there will be two cases. Since there is temperature here, there will be two cases. So case 1, okay, case 1 at T is equal to 0 Kelvin, at T is equal to 0 Kelvin. At T is equal to 0 Kelvin, what happens? FEI will become what? FEI will be definitely, I mean, the at T is equal to 0 means 1 by 0 is infinity, so e to the power infinity. Now it depends. Now if this EI is greater than EF, okay, achha, EF is what? EF did I mention? EF is the Fermi energy. EF is the Fermi. What is the Fermi energy? I will describe now. Okay, EF is the Fermi energy. Achha, if EI is greater than EF, then what do you have here? Then you have the, I mean, e to the power of EI is greater than EF and T is 0. So e to the power of plus infinity plus 1. So e to the power plus infinity means basically plus infinity. So when in the lower is infinity, the 1 by infinity is 0. Okay, and if here EI is less than EF, EI is less than EF, then what will you get? Then you will get FEI will be equal to e to the power of minus infinity plus 1. So e to the power minus infinity is 1 by infinity. So the 0, 1 by infinity is 0 plus 1. So this will be 1. Okay, this will be 1. So from here, what will be the graph now? If you plot, the graph will be just a step function like this. It will just be a simple step function like this. It will be just be a perfect rectangle. I couldn't draw it like that. Okay, it will be a step function, and here this one will be what? This point will be EI is equal to EF. Okay, this point will be EI is equal to EF. This point will be FEI is equal to 1. Okay, so what are you seeing here? So this graph is for T is equal to 0 Kelvin. So what are you seeing here? At T is equal to 0 Kelvin, the graph becomes basically a step function. That is, till the energy is within EF, that is less than EF, the FEI is equal to 1, and after just after EI is greater than EF, it becomes 0. Here this portion is basically 0. Okay, this portion is basically 0. So this is the thing, that is till till EF, that is the Fermi energy, all the energy states are occupied. This is called, all the energy states are occupied, and above the Fermi energy all the energy states are empty. Okay, so what can you write here? That at absolute zero temperature, all possible quantum states of energy, all possible quantum states of energy less than EF, that is Fermi energy, are occupied. Okay, and all those of energy, more than EF are empty. Okay, are empty. So from here, what can you tell about the what can be the definition of Fermi energy? What can be the definition of Fermi energy? So this is the Fermi energy. So till Fermi energy at 0 Kelvin, till Fermi energy all the energy states are occupied, and above it all the energy states are empty. So so you can write here that Fermi energy EF is defined as the energy, Fermi energy EF is defined as the energy of the highest occupied level at absolute zero. Okay, highest occupied level at absolute zero. This is very important. Fermi energy is defined as the highest occupied level at absolute zero. Okay. At absolute zero temperature, you are seeing here at absolute zero temperature, when EI is less than EF, the EI is greater than EF, all the energy states are empty. FEI, there is no probability. Probability is zero of occupation. Probability of occupation of the energy states is zero. But whereas it's below Fermi energy, probability is 1. 1 means all are occupied. FEI is 1 means all are occupied. This is FEI is what? FEI is probability. And FEI is 0 means but there is no probability. Probability is 0. Okay, so the probability that all are occupied is 1, and the probability is 0 means all are completely unoccupied. So here this is the Fermi energy, that is the defined as the energy of the highest occupied level at absolute zero. Okay, it is the energy of the highest occupied level at highest occupied level. Definitely this is the highest occupied level. After this level, the energy starts from what? Energy, this is 0 0, this is the origin. So energy starts from 0 1 2 3 4 5 6 like the till EF. So EF is the highest occupied level. So till below EF all are occupied, above EF all are empty. Okay, so Fermi energy is defined as the energy of the highest occupied level at absolute zero. And then if you do case 2, case 2, okay, at T greater than 0 Kelvin, T greater than 0 Kelvin, what will you have at T greater than 0 Kelvin? T greater than 0 Kelvin, you come here, FEI will be what? FEI is equal to 1 by e to the power of EI minus EF. So EI minus EF, T is finite. Okay, T is finite here. So this will be a positive quantity. Okay, this will be a positive quantity. Now here, say at T is greater than 0 Kelvin, if EI is equal to EF, then what will you get? FEI will be what? FEI will be 1 by EI is equal to EF, so 0. So e to the power 0 is 1, so 1 by e to the power of 0 plus 1. So e to the power 0 is 1 by 1 plus 1 is 2. Okay, so here what will you get? So when T is greater than 0 Kelvin, if EI is equal to EF, then FEI equal to half. Okay, so from here also you can define the Fermi energy, or the Fermi energy EF at temperature greater than 0 Kelvin is defined as the energy at which the probability of occupation is half. That is 50% of the energy states are occupied and 50% are empty. Okay, now when will this happen? This will happen, see here, say this is 1, okay, this region is 1, and say almost half here. This is half. Okay, so this is what? This is half. Okay, so here how will the graph change? Okay, how will the graph change here? Now at T is equal to 0 Kelvin, it was just a step function. So how will the graph change now? Now say let us take a temperature T2, which is, or say T1, which is greater than 0 Kelvin. Okay, let us take a temperature T1 which is greater than 0 Kelvin. Okay, so how will the graph look like? Now it will be like this. Okay, it will be like this. This will be like this. So this one will be T1 Kelvin, this one will be T2 Kelvin, and 0 is less than T1 is less than T2. Okay, like this it will be. 0 is less than T1 is less than T2. Okay, so this will be the thing. So the graph will change in this way, that is and so this thing, that is say this much thing, in this case, say in this case, that is this is T2, so this is T2. This is T2. Okay, I did a little bit wrong here. Actually, this one will be T1. Okay, this one will be T1 Kelvin, and this one will be T2 Kelvin. This one will be T1 Kelvin, and this one will be T2 Kelvin. So in this case, this one will be this this much interval. This much interval will be what? This much interval will be KB into T1. Okay, this one will be KB into T1. Similarly, this interval will be Similarly, this interval will be kb into T2. This interval will be kb into T2. Okay, this is the thermal energy. Okay, so this is the thing. This relation is the same. My T2 is greater than T1, so kBT is also definitely kBT2 is greater than kBT1 only. Okay, so this is the thing. Okay, so from here what you can tell? So what you can tell is at a temperature greater than 0 Kelvin, the best definition of Fermi energy is this one only. That is, the Fermi energy is defined as the energy of the highest occupied level at absolute 0 Kelvin. At absolute 0 is also right. Okay, now suppose that temperature higher than 0 Kelvin, okay, at a finite temperature, what you will get? At finite temperature, Fermi energy of a system is that energy for which 50% energy states are filled and 50% are vacant. Okay, 50% of the energy states are filled and 50% are vacant. Okay, that is the Fermi energy. So how you can write here like that? You can write like this, that at a finite temperature, finite temperature Fermi energy of a system at a finite temperature, Fermi energy of a system is that energy at a finite temperature. Fermi energy of a system is that energy for which 50% energy states are filled, okay, and 50% are empty or vacant. Okay, empty or vacant. 50% of the energy states are filled and 50% are empty or vacant at a finite temperature. Not 0 Kelvin. At 0 Kelvin, what is Fermi energy? It is the energy of the highest occupied level at 0 Kelvin. Okay, but at finite temperature, Fermi energy of a system is that energy for which 50% of the energy states are filled and 50% are empty or vacant. Okay. So now, and what is Fermi level? Fermi energy and Fermi level is the level of the at which the is the level of the highest occupied energy level. Okay, Fermi level is the level of the highest occupied energy level at 0 Kelvin. Fermi level is the highest occupied energy level at 0 Kelvin. Okay, now now comes example. You have done particle in a one-dimensional potential well. So what do you have there? You have, this is the ground state energy. Okay, then there is the first excited state, then there is the second excited state, third excited state, like this. So gradually the states increase. Okay, now this is n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5. Let's say T is 0 Kelvin. Okay, T is 0 Kelvin. Now say you have electron. So here there will be, suppose, one electron. Okay, here there will be, say, another electron. Here there will be another electron. Here there will be another electron. There are, suppose, 4 electrons. Okay, there are suppose 4 electrons. Now what will you tell? That I mean, since it obeys Pauli exclusion principle, so no 2 electrons can be in the same energy state, same energy level. Okay, so in this way the electrons are arranged. Now I mean, n is equal to 4. After n is equal to 4, since there are no electrons, I mean, you cannot arrange anything more. But there are energy levels above this also. There are energy levels above this also. All these are empty. So what will you tell here? In this case, in this particular case, the E4 is the actually Fermi energy. In this case, E4 is the Fermi energy. E4 is the Fermi energy, and n is equal to 4 is the Fermi level. N is equal to 4 is the Fermi level. N is equal to 4 is the highest occupied energy. Okay, so this is the Fermi, I mean, Fermi concept of Fermi energy and Fermi level. Now the best example of the to understand this is your all of you have done semiconductor. Suppose you take an intrinsic semiconductor. You take an intrinsic semiconductor. Okay, you take an intrinsic semiconductor. In intrinsic semiconductor, what do you have? You have a valence band. Okay, you have valence band, and you have the conduction band. You have valence band and you have conduction band. Now what happens at say T is equal to 0 Kelvin? T is equal to 0 Kelvin. So in intrinsic semiconductor, what happens? This is the valence band and this is the conduction band. Where is the Fermi level? The Fermi level lies almost at the middle of these two bands. Okay, the Fermi level lies almost at the middle of these two bands. Okay, so this is the Fermi level, EF. This is the Fermi level. Now I mean, at T is equal to 0 Kelvin, you see here this is completely empty. Conduction band is completely empty, and you have all the holes here like this. You have all the holes here. You have all the holes here. Hole, 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 hole. Okay, all the holes. The valence band is completely full. Okay, and till the Fermi level it is completely full, and above the Fermi level it is completely empty. Okay, now at say if the temperature becomes little bit high, temperature becomes higher, then gradually what will happen? Some I mean some holes will go from the valence band to the conduction band, then some little bit conduction will take place. Okay, but at T is equal to 0 Kelvin, this conduction band is empty, valence band is filled up till the Fermi level. Okay, achha, what happens for extrinsic semiconductor? In extrinsic semiconductor, what happens? In extrinsic semiconductor, say for p-type semiconductor, for p-type semiconductor what happens? For p-type semiconductor, this is the conduction band, this is the valence band. Okay, here there are holes, there are p-type, this is a p-type semiconductor. Here there are lot many holes because you have been doped holes here. You have doped holes, p-type impurity you have doped here. So there are a lot of number of holes. Okay, so there are a lot of holes here. Now there are some electrons also here because of the I mean thermal effect. Some has gone. Take it for T is greater than 0 Kelvin. Here what will happen? The Fermi level will lie somewhere near to the valence band. Somewhere near to the valence band, the Fermi level will lie. And for n-type, what will happen? For n-type, this is the conduction band. Now here there will be a lot number of electrons will be here because you have doped electrons, you have doped n-type impurity. Okay, you have doped here n-type impurity. N-type impurity is doped here. Okay, so and here there are, this is the valence band, this is conduction band, this is the valence band. In valence band you have got holes, you have got little bit number of holes. Okay, so here now the Fermi level will be at this position. Okay, so this only I want to say. Now what will happen when you will make a PN type of junction? When these two p and n type semiconductor are joined, you make a junction. What will happen for the for the conservation of energy principle? So these things, this you have to make it in such a way. In this case, the Fermi level will go up for this case, and n type will go down. So there will be a this kind of thing will happen. A bending will happen. Okay, a bending like this will happen. This kind of bending will happen. Okay, now in this bending, what will happen here? Now in this case, where will the Fermi level lie? Actually, this should have been little bit up. Fermi level will be like this. Okay, actually this should have been symmetric. Acha, so I mean this is the what? This is the P region and this is the N region. Okay. So here you see this is the P region, this is the N region, and this is the conduction band, this is the valence band. Okay, so this is the Fermi level EF. Okay, this is the N side and this is the P side, and so now you see here there will be the energy levels. Okay, now here there is a trick you need to understand. Now how are the energy levels spaced? I mean, closer to the Fermi level, the energy levels are, the density of the energy level is not that much. If you see the from the internet, if you see the hydrogen atom level, okay, so for that case, if you see the particle in a one-dimensional potential box also, for a hydrogen atom level, if you see, the hydrogen atom levels are like this. So here there is the n is equal to 1. Okay, then there is here n is equal to 2. So see, they are very distantly spaced. Then there is gradually the energy difference decreases. N is equal to 3. Then there is n is equal to 4. Then there is n is equal to 5, like this, and ultimately at high n like this, they become very, at high n they become very densely spaced. At high n they become very densely spaced. Okay, as the n number, at higher energy levels they are densely spaced. Okay, so similarly here also that thing happens. There is at these levels, the energy levels and the density of the energy levels is less. Okay, the density of the energy levels are less here. Now here they are very densely spaced. But on the other hand, at here near the Fermi level, near the Fermi level, the population of the electrons or the holes are also more. Okay, so what happens here is that uh, what happens here is that if suppose there is an electron here, if suppose an electron is here, the electron tries to move towards the, this is the depletion region, this is the depletion region, this is the depletion region. Okay, now if the electron wants to move here, there is a barrier, quantum mechanics, I mean it cannot pass this barrier. But if the electron is here at this in this level, if the electron is there, this electron can easily pass here. Okay, so similarly here also the same thing happens. Here also in the valence band also, these are bands. You must learn how the bands are formed in a solid. Okay, that can be asked in your viva. For this, you have got how to find out the band gap energy by two probe method. In that experiment, that can be asked. So here near the Fermi level, the density of the energy states is very less. Okay, gradually the density increases, but here the electrons density is more, so rather here holes. So if a hole wants to move from here to here, it cannot move, but if a hole is here, it can move pass very easily. Okay, so this is the thing. I mean this is the thing actually. Okay, so today up till this one only I am doing. I will continue the next in the next class.